Okay, let us start. So last time we started talking about discrete symmetries. So if you have a complex scalar theory, and then in addition to a U1 symmetry, there are also discrete, classically there are also discrete symmetries. First is parity. So we normally denote with a symbol P and act on x mu by t, take it to minus x. Okay? So you just flip all the spatial direction. And you also have time reversal. Okay, time reversal, and then I normally write as a script t on x mu, then take to the minus t and x. Okay, does not do anything with x. And then we also have a charge conjugation. Charge conjugation, which takes phi, goes to phi star. Okay? And so, of course, our goal is to understand this, those symmetries at quantum level. Okay, so at quantum level, so you already then in quantum mechanics, in quantum mechanics, symmetries are implemented. Symmetry transformations, so they are corresponding to unitary. Okay, transformations, okay? Okay, they correspond to unitary transformation. We already have done that for continuous symmetries. And the same thing is with the discrete symmetries. And in quantum mechanics, the implementation of the discrete symmetries are also through some unitary operator. And so there's a slight subtlety with the time reversal. Because all the other symmetry transformations corresponding to the unitary transformations, except for the time reversal, are actually corresponding to the anti-unitary transformations. So have you seen that in quantum mechanics? Okay, let me just review it here. So previously I want to say recall, but it says we don't have to recall it. So let's denote the ut as the unitary operator. So this is a unitary operator for time reversal. Okay, and then the claim is that this should be antilinear. And it's not actually ordinary unitary, it's called anti-unitary. Okay? And so now let's try to explain where those things come from. So suppose that you have a system which we say is time reversal invariant. So by definition, the symmetry is that the corresponding transformation of the symmetry should commute with your Hamiltonian. Okay, so this is what we mean by the system to be time reversal invariant. Okay. So here I'm just talking about just in quantum mechanics. Okay, let's not even worry about the field theory. So now, suppose we have a time reversal invariant system. Which the time reversal operator commutes with your Hamiltonian. And then let's act this ut on the wave function. Okay, then you get some psi prime. So by time reversal, we expect physically, okay? So physically, we expect if psi satisfies the standard Schrodinger equation, and then psi prime should satisfy the Schrodinger equation with t goes to minus t, okay? It's the same Schrodinger equation. But with t goes to minus t. Okay, so that's what we mean by time reversal, okay? So now let's try to do that. So let's start this equation. And now let's just act by UH from the left on this equation, okay? So the left-hand side have UH. Yeah, means that, before I leave it do one more step. Which means that the psi prime should satisfy the following equation. Okay, so you just take t goes to minus t, and then you get additional minus sign. Okay, so so psi prime should satisfy this equation. So now let's see how to get this equation. Now let's see how to get this equation from here by using this relation. Okay, by using this relation. So this is simple. Let's just act a u on the left of this equation. So let me call this equation star, and the equation star. So if I act ut on star, then on the right-hand side, is ut commute with h. Okay, so on the right-hand side, we just directly get ut h psi, and we can just commute them. So this is the same as h psi ut, ut psi, and this is just psi prime. So the right-hand side just gets psi prime, okay? And left-hand side, you get ut I partial t psi. Okay? So in the ordinary situation, we would have trouble. So if you, because this is the operator, I is a C number, and the partial t is some number, so you can just directly pass through this I and the partial t. When ut act on psi, then you get the same equation, rather than the equation with minus sign. Okay, then you have trouble. And the only way to get that equation is to require when ut pass through I, take it to minus I. Okay, we impose this condition. When ut pass through I, you get the minus I. Okay? So this means, so we can define antilinear operator. Antilinear operator is defined to be the following. Means that if you have some operator A act on some number C, when you pass through that number C, you get C star A. Okay? So the antilinear operator A is defined to be have this property, and C is just ordinary C number. Okay, ordinary C number. So you see here, ut tells you in order for ut to be really to be a time reversal operator, and ut had to be antilinear. Okay, so that when you pass through I, takes I equal to minus I, because the minus I is a complex conjugate of I. Okay, good. Any questions on this? Good. So yeah, so UT should be antilinear. Okay. So also for antilinear operator, the joint should be defined differently. Yes.
So we started off with trying to show star-star using how UT acts on psi, but then we kind of inserted this requirement ad hoc to satisfy.
That's right. That's right.
So a bit confused. Then how do you come up? Why would star-star need to be true?
No, star-star is the definition of time reversal, right? Star by star, star-star is what physically we mean by time reversal. If you want something to implement the time reversal, it has to achieve a star-star. Yeah. Other questions? Okay, good. And then we derived that in order to achieve the time reversal, then UT has to be antilinear. And because antilinear has this weird, antilinear operator has this weird property, the joint of antilinear operator, the definition should also be changed. Okay, so the joint of antilinear operator linear operator A is defined to be, say, if you have psi, A dagger, chi, okay? If A is ordinary operator, and then the definition of the joint is that this is equal to A psi chi. Okay, so this is a standard definition. Yes?
Yeah, so I'm a bit confused about how you deal with making multiplication, scalar multiplication non-commutative. And I was wondering, why couldn't you, would it make sense to just say that UT and H can be true?
UT and H anti-commute. So by taking the yeah, you can also do that. It just does not work as well. Yeah, you see whatever it works. Yeah, yeah. It's much easier just to make the UT to be antilinear. Yeah, right. Yeah, yeah. For this particular equation, it can work, but then you have to be against the principle. Somehow H commute with the symmetry. Yeah, yeah. That is considered to be most accurate principle. Yeah. Other questions? And indeed, yeah, right. Okay, good. So the way we define the joint should also be different. So this is standard definition. So for antilinear, you have this definition, then you put additional star. Okay? You put additional star. And the reason you put additional star is precisely due to that this property. Okay? Because remember, if you put the complex conjugates, put the C number here, and then you should be able to take the C number outside the this kind of overlap. But in order to be compatible with the property of the antilinear operator, and then you have to define the joint to be this way, so that you have a consistent story. Okay. Yes, I will leave it to you yourself as an exercise to show actually this is actually the right definition. Okay. And then we can define the anti-unitary as that if you have operator with anti-unitary means u psi, u chi. So standard unitary condition, just this is equal to chi and the psi and the chi. Okay. And now for the anti-unitary, again, you just put a star. Okay, just put a star. And so the claim, okay, so the claim is that the UT, the time reversal operator should be an anti-unitary operator, okay, in order to be a symmetry. Okay, so this is just a brief review of this time reversal in quantum mechanics. So now let's look at the the quantum version of those symmetries in quantum field theory. Okay, so first let's do the as warm up. Before let's do it for the Dirac theory. Let's do it warm up for complex scalar fields, which is much simpler. Okay. So this theory, the action is invariant, we said, under those symmetries. Okay, if we just flip the spatial direction, clearly that Lagrange is invariant. You flip the time direction because the time derivative is quadratic, it's also invariant. And again, if you change phi to phi star, the Lagrange is invariant. Okay. So quantum mechanically, so those symmetries should be implemented by some unitary operator. Okay. So now the parity transformation on the field should corresponding to, you start with phi x, and then you go to phi prime x. So phi prime x should be equal to phi px. Okay, this means that the and then put, yeah, you can also put the phase here. Okay, so you can show that this transformation certainly is a symmetry of this Lagrangian. Okay, yeah, because as I said, if you just flip it, it does not change anything, but you can also put arbitrary phase here in principle. Okay, you can in principle put arbitrary phase here. Because anything, they all only depend on the phi and phi dagger. Okay, and so this is P and this is the T, then corresponding to phi x, then goes to some phi prime x equal to, again, some phase, say phi tx. Okay, and then the charge conjugation normally is called C. So parity is normally called P. Okay, so here it's corresponding to phi x goes to phi prime x equal to eta C phi star x. Okay. So in each case, such kind of transformation should be generated by some unitary operator. So for example, this should be generated by UP phi x UP dagger. Okay. And similarly for this one, we call it UT dagger, and here UC and UC dagger, similarly. Okay. So the quantum level, they should be generated by some action of some unitary operator. Yes?
Do you always have this nuance symmetry, or do you have the such interaction theories where you have one power of phi, but you don't have?
Sorry?
So you can add arbitrary phase?
No, I'm going to talk about the phase. Okay, I'm going to talk about the phase. So if you are even looking at that Lagrangian, and then you see you put the phase, this is invariant. Okay. But now the question is, can those phases be arbitrary? Okay, the question is that can those phases be arbitrary? So in the case of this complex scalar, actually should not be. So let's use the example of the parity. So we know that when you do parity twice, okay, if you do parity twice, you should go back to your original. Yeah, your system does not change. Okay, if you just do reflection twice, your system does not change. So that means that when you do this twice, you should you haven't changed anything at all. Okay, so when you do it twice, the phi should come back to itself. And indeed, this p square, if you do it twice, come back to itself. But then this phase should also come back to itself. Okay, so that means that the eta p square should be equal to 1. Okay. So if you want the symmetry to come back to itself, and then eta p then can only be plus minus 1. But it can be minus 1. Okay, it does not have to be plus 1. So we call when eta p is equal to +1, we call it a scalar. When eta p is a -1, we call it a pseudoscalar. We call it pseudoscalar. Okay. And similarly, a similar thing can be said about the eta t and eta c. Okay. So by definition, this unitary operator act on phi should act as this. So now we can, and now remember the phi is expressed in terms of the creation and annihilation operators. Okay. So by requiring, yes? No, they don't have to be. No, they don't have to be. Yeah, they can be. Say this equal to 1, eta p can be -1. Yeah, they don't have to be. Yeah. Yes.
Can you say like if eta is one scalar in what sense, I guess?
Huh?
Is scalar in what sense? Especially if like the other etas don't have to follow. Like I don't understand what is a scalar if eta is equal to 1.
We just say it's a convention, it's a lane. Yeah, we just want to distinguish these two cases. So this is, so when you say it's a scalar, we should say this is an ordinary scalar, and this is called a pseudoscalar. Yeah. We just want to distinguish these two cases. Yeah. Other questions? Yes? Yeah. Yeah, so it just getting complicated. You can invent, you can try to invent 8 names for this. There are 8 possibilities, and the people normally don't bother to invent 8 names for it. And since the parity is often used, and so they they just talk about the parity. Okay, they just define this way. We normally don't give a name. Let's say in this case, yeah. You just specify it whether it's 1 or -1. And so the reason we give a name for this because of the pion and pion are pseudoscalars. Okay, they actually transform under the parity by minus sign. The Higgs will be the ordinary scalar. They transform as 1. Good. So far I have this expansion. So by requiring up phi dagger, phi x, phi up dagger equal to that thing, yeah, equal to this, say, plus minus eta p phi px. So by requiring this, we can work out how up act on A and B. Okay, we can work out how up worked on A and B. So you find that the parity acting on AK, up dagger, equal to the same eta p factor, and then take it to A minus K. Okay, so this makes complete sense because because we interpret K as momentum, right? So so under reflection of a spatial direction, your momentum also changes direction. And so it takes AK equal to A minus K. And similarly, you can work it out, the UT acting on AK, UT dagger, give you eta T, also A minus K. Okay? And similarly with the BK, okay? So this also makes sense. When you revert your time direction, your momentum also changes sign, okay? Your momentum also changes sign. So now the charge conjugation is a little bit more interesting. Okay, so the UC for the charge conjugation is a little bit more interesting. So the charge conjugation takes AK dagger equal to eta C equal to B. Okay, and similarly takes the So you see that what this charge conjugation does is to exchange particle and antiparticle. Okay, exchange particle and antiparticle. Good. Any questions on this scalar field? Good. So now let's look at the with this scalar field story. Now we can look at the Dirac field, which is more intricate. Okay, which is more intricate. So let's write down the. So let's forget about the previous scene. Let's write down the action for the Dirac theory. Okay, and then let's also write down its equation motion. Okay, now let me call this equation star, erase the earlier star. So now let's first understand how the parity should act on the Dirac field. Okay. So now as everything with the Dirac field slowly become tricky, okay? Become tricky. So naively, if you want to just try to generalize the scalar story, we say let's imagine the Dirac field should transform okay, and this to say for the parity, for example, to psi px. Okay, with some phase. Okay, maybe with some phase. So if you want to naively generalize to the scalar story, that would be you do. Okay, that should how the parity transform. But now remember, psi now is a 4 vector. Nobody tells you that under parity, the different component of this 4 vector cannot get reshuffled. Okay, remember under Lorentz transformation, they do get reshuffled. Okay, a Lorentz transformation, remember for spinner, Lorentz transformation not only acts on X, but also on the internal space of the spinners. So you would expect the most general parity transformation should also act on the internal space. Okay, so you would expect the phase is not enough. So we actually have to put a matrix here. So let's call it D. So, and whatever phase will be absorbed in this D, okay? Of course, you also include phase. And yeah, so for rotation convenience, I will also write it as psi prime x prime equal to d psi x. Okay, so the x prime equal to px. Okay, so these two are the same equation. Okay. So D, and just write D is a matrix. Acting on spinner space. Okay. So in what sense we say the Dirac theory is parity invariant? Okay, let me just formulate it in terms of the equation motion. You can also equivalently formulate it in terms of the action. Okay. Yes? We will talk about the behavior. This is a good question. It does not have to, and we will talk about the property of D. Yeah. Do you have other questions? Good. So what do we mean by the theory is parity invariant? Okay, by the theory, we say the theory Dirac theory is parity invariant. We say this Dirac theory have a parity symmetry. You can always define a parity operation. When we say a Dirac equation have a parity symmetry, means that if we start with a psi which satisfies the Dirac equation, and then there should exist a D, such a D, okay, such a matrix, such a transformation, so that this transformed the psi still satisfies the Dirac equation, but in the reflected space. Okay, so you want to reflect. So x prime corresponding to the reflected space, and we say the theory have a parity symmetry means in the reflected space you should have the same equation. Okay, you should have the same form of the equation. So that means that this psi prime, when you're writing it in the reflected space, should have the same form of the equation as the original Dirac equation. So this is the same concept as this covariance, Lorentz covariance we described earlier. Okay. Yes.
Why doesn't the parity transform act on the gamma matrices? Because we changed d mu inside, but not the gamma.
Yeah. Gamma matrix is just some numbers, right? Because gamma matrix is always just some numbers. They're not space-time variables, so they're not. So they don't change under the parity. Yeah. Other questions? Yes.
Is there like any reason why D has to be like a matrix? Why this has to be linear?
No, D does not have to be a matrix. I'm just to say D can be a matrix, but we want to find the D so that we have this. But D can be identity.
There could be some complicated function that's nonlinear. Because we already allowed for nonlinear like time reversal operators. So
The time reversal is linear, right? Time reversal is linear. Yeah. The action of normally action of this kind of you just go to psi itself, but you can You're asking why not we why we don't use a red psi square term, or you are asking whether the D can depend on space time. Which one are you asking?
yeah, I meant like f of psi, like some arbitrary function of psi.
Yeah, but this is the simplest one. Yeah. If we can make this work, then you don't have to do that. Yeah, you first do the simplest one first. Also, we do believe that this kind of parity operation should be a linear operation. Yeah. If you add the two operators together, you do the parity, and you should after you do the parity, should be still the add sum together. If it's a nonlinear function, then you won't satisfy that property. Yeah, just from our experience, just physically we expect the parity to be a linear operation. Good. Okay, so we want to find the D so that this is satisfied. Okay, so that means that the so this is easy. So now let's just look at this equation a bit. Okay, so let's write it more explicitly. So partial mu prime. Yeah, so we write this explicitly. So partial 0 prime is the same as original partial prime because you don't flip the time direction. Okay, and then you flip the spatial direction, so that means this becomes partial I, gamma I, partial I. And so I remove the prime, but I have a minus sign here. Okay, because you change sign. And the minus n, And this one, from our definition, should be equal to this. So this is just equal to d psi x. Okay? Okay? So now if you compare with this equation, so if you compare with this equation, now let's add the d on this equation. So that's corresponding to d gamma 0, partial 0, plus gamma I, partial I, minus n psi x equal to 0. Okay, so this is the original equation. And now we want these two equations to be equivalent. Okay, because given this equation, we should have that equation. Okay, and so we want these two equations to be equivalent. So in order for them to be equivalent, you see the last term is the same because m is just number commute with d. And then in order for these two equations to be the same, we want d commutes. It means that d should commute with gamma 0, but anti-commutes with gamma I. Okay? Because when you pass through here to bring it to that side of gamma I, you should change the sign. Okay. So now you can immediately write down such a. So now you can immediately write down such a matrix. Then D has to be. It commutes with gamma 0 and it commutes with gamma I, so it has to be proportional to gamma 0. Okay? And then you can put a phase here. Okay. And you can put a phase here. So this is how it transforms. So now you can further constrain eta p. Now you can further constrain eta p. But here the story is a little bit subtle. We will not go into there. So you said the fermion. Remember when we already discussed in your quantum mechanics, when you have a spin half particle, when you rotate 360 degrees, you actually don't have to go back to itself. You can go back with a minus sign. Okay. And so here so here so there's an intricate story you can discuss what allowed eta p. And so we will not go into that. But I think you know the basic idea. Okay. Good. Any questions? Yes?
So wouldn't this just like if one of these two equations to be equivalent, that could be satisfied if gamma 0 is real and gamma I is pure imaginary because of this antilinear? Or is that?
Wait, what do you mean by no? This equation should be applied for any gamma 0, any gamma I. No, you cannot. Yeah, because parity you should work in any representation. Okay. So this is the story for the parity. So completely similar idea for charge conjugation and the time reversal for fermions. And so I will do it a little bit faster. Okay, so I will do a little bit faster. Mostly again just outline the same idea, but then just write down the results. So for the charge conjugation, so now let's do the charge conjugation. Did I say? Yeah, sorry. Here I should put a thing here with parity. So we are doing parity here. So now let's do the charge conjugation. So for the scalar case, so the charge conjugation just take the phi star. Again, so for the Dirac field, for psi prime, again this should be proportional to phi star. Okay, to phi star. But so a simple way to construct phi star is you take the psi bar, okay, and then you take a transpose, okay. And so this is the some linear combination of the phi star. And also you should, from what we discussed before, you should allow a matrix here. Okay, you should allow a matrix here. And the C again is a matrix in the spinor space, okay. And now again we need, so the statement of the charge conjugation is the statement that given is exists C, there exists C such that given equation star, that psi prime satisfies the same equation. Okay, psi prime satisfies the same equation. Okay. So so we just do it. Okay, so we just start from here. So since the psi prime are related by psi by taking the bar and the compressed and transpose, so let's then first do the bar for this equation and then do the transpose. Okay, so when you do the bar operation from that equation, so the star, then give the bar equation satisfied by psi bar. Yeah, you can easily check yourself. 0. Okay, now you do a transpose, and then you get gamma mu t partial mu plus n. T. Okay. So and psi bar t is just equal to c minus 1 psi prime x equal to 0, okay, because from here by definition, okay. So now you want this equation to be equivalent to that equation. Okay, so as we do before, a similar idea from that, okay, you just act c prime, c minus prime here, okay. So in the end, you conclude that the gamma mu t, so from here, equivalence of these two equations, you conclude that the gamma mu t should be related to gamma mu by this C matrix. Okay, like this. So if you can find the C satisfies this equation, and then they are equivalent. Okay? Okay? So does such a matrix C exist? So we can say actually such a matrix C always exists for the following reason. Because you can check given gamma mu satisfy this, say this Clifford algebra for gamma matrices, and the minus gamma mu t and minus gamma mu t also satisfy the same algebra. Okay, so this will do that. So that means the minus gamma mu t, okay, is also allowed a set of gamma matrices. Okay, because they satisfy the same algebra. And now we discussed before, mathematically can prove all representations of the gamma matrix are equivalent. Then that means there must exist some matrix C which relates to these two. Okay, and C must exist. Okay, so this tells you C must exist. So now it's not so easy to write down the C explicitly as in this case. Okay, so here we can write the expression for D regardless the choice of gamma matrices. And here it's actually not so easy to write the explicit form of C. Okay, so of course for specific choice of representation of gamma, you can write down C. Okay, but it's enough for us to know that C exists. Okay, and then this is the transformation for the charge conservation. Okay, it's the transform this way with C satisfy this condition. Okay, C satisfy this condition. Are there any questions on this? Okay, good. And then we talk about time reversal. The idea is again similar. So now we use UT. Okay. So now we suppose with the psi prime is equal to some matrix, and then psi Tx. Okay, this is the direct analog of the this transformation. Okay, and the same as the psi prime x prime equal to dt psi x, and now x prime equal to t act on x. Okay, you just flip the time direction. Okay, just flip the time direction. And now again the statement of the time reversal. Again, the statement of the time reversal. Now the statement of the time reversal is that the given star then it's again that the gamma mu partial mu prime minus m then equal to psi prime x prime equal to 0. Okay? Okay, in this new frame equal to 0. Okay. And then the story will be similar. Okay, the story will be similar. What you can, and then just again try to match starting from that equation, and then you try to match those equations. Okay, so we're not going into detail. And in the end, you find that the dt should satisfy this equation. Okay, so you find dt should satisfy this equation. Gamma mu t again gamma mu transpose is equal to dt transpose gamma mu dt minus 1 transpose. Okay, so gamma mu t has to satisfy this equation. Okay, so now if you compare these two equations and this equation, they just differ by a minus sign. Okay, they just differ by a minus sign. So we conclude that we can do this by taking dt transpose equal to c minus 1 gamma phi. So the gamma phi will generate this minus sign when you commute with gamma mu, and then that accounts for the actual minus sign. That accounts for the actual minus. So if you know C, then you also know this time translation. symmetry matrix. Okay. Yes. Yeah. Because only the operator itself, only U, is antilinear, right? D just corresponding to the specific matrix acting on the spinor space, and so that's just ordinary matrix. Yeah, DT just ordinary numbers made up from gamma matrices. Yeah. Other questions? Yes.
So parity corresponds to reflections in space.
Yeah.
And time reversal is like a reflection in time.
Yeah.
So like, can you like boost into like space time if you make a Lorentz boost to space reflection, then
No, you cannot relate these two. They are independent discrete transformations, are not related to a boost. Yeah, not related by a boost. Yeah, if they are related by boost, then we should only to worry about one of them, because the boost you already understood. Yeah, so they are independent discrete transformations. Yeah, not related by any other continuous transformation. Other questions? Yes?
There's only one parity transformation no matter the dimension, right?
Yeah, that's right. Yeah. Just in any dimension you have this one. Yeah. Good. Okay. Yes?
Yeah, I don't know if this makes sense, but is it possible to have a situation where in one frame a quantity is conserved to a parity or a time reversal transformation, but then in a Lorentz boosted frame that's different, then one of those quantities is conserved, or if it's conserved in one, it's conserved in all?
Yeah. It's if it's conserved in one, it's conserved in all of them. Yeah, it's because the conservation equation is a covariant equation. Yeah, because the conservation equation is partial mu j mu equal to 0. So this equation has the same form in any frame. Yeah, but the charge is different in different frames. Yeah, they're related by transformation. Yeah, just in any frame you can define a charge, conserved charge. Good. Okay. So now let's move on to the next topic. So now finally we talk about path integrals for fermions. And with path integrals, then we can do interactions. Okay, remember when we know how to do path integral for scalar, then we can easily do interactions. And now let's do the path integral for fermions. And then that will give us a very simple way to treat interacting series. Okay. So let's just recall in the path integral we considered before. So if you have ordinary quantum mechanics, so you have x and p commutator equal to I, and then the path integral you just you integrate over all configurations of xt. Okay, so that's what you do in quantum mechanics. So now xt is just ordinary function. Okay, you just integrate over all possible trajectories, and xt is just ordinary function. So now when we go to quantum field theory, then we have phi, then commute with, yeah. So let me just put a hat just to show, to emphasize these are operators. And the phi, we have tx, and then we have pi phi, the conjugate momentum. And again, this is equal to I something, okay, the delta function, okay? Okay, this is I, and then you have delta function. And then when we do the path integral, we just integrate over all configurations of phi xt. And now this is just a classical field. Now essentially you view this just as an ordinary function, okay? You integrate just all possible value of it. Okay, all possible functions of it. Okay, all possible functions of phi. So now we have to do fermions. We have to do psi. So psi is a little bit weird because as we discussed before, the psi, you no longer have the commutator, you actually have an anti-commutator. Okay? So what do you do? Okay, do you still following the same rule, or you actually have to change the rule? Okay? So that actually was a question which, so Fermion actually, he came up with this idea of a path integral in 1948. And then, of course, generalization to scalar will be immediate. Okay. But then he wanted to generalize to fermions. But then for a long time, he couldn't do it. If you just use this method to do for fermions, and they just didn't work. Okay, we will not go through that exercise. If you does this for fermion, it just does not work. So for many years, he couldn't find the answer. But then around 1962, I think it's 1962 or 1965. Anyway, just around some early 1960s, and a former Soviet physicist actually came up with a brilliant idea to solve this problem. Okay, and like 15 years later, after the discovery of path integral, and so the basic idea is that when you have a Dirac field, so when you have a Dirac field, then you have anti-commutation relation, psi, and pi psi is anti-commutation relation now, okay? It's an anti-commutator. And then this guy called Berezin then postulates that when you do the path integral, what is in the path integral will be analog of the classical version of this field, okay? The classical version of this operator. So then what would be the classical version of this anti-commutator? And he just written it just should be some quantities which anti-commute. Okay? So classically, maybe say classically put a quote, because we only do this in the path integral. And then corresponding to anti-commute fields, the object. Okay? And then when you do the path integral, you just integrate over psi, but psi is an anti-commuting object. Okay, turns out that this just brilliantly solves the problem. Okay, it just immediately works. Very simple. So in hindsight, it's extremely simple, but actually, Fermion couldn't figure it out himself. Okay. Right. Anyway, so now let's talk a little bit about this anti-commuting object. Okay. So these are called Grassmann variables or numbers. So this Grassmann object, they just anti-commute, okay? So they even anti-commute with themselves. So if you anti-commute with yourself, then the only thing you can have is that theta square, there must be 0. Okay, if you have an anti-commuting object theta, and if you can anti-commute itself, will be equal to 0, because theta square should be equal to minus theta square, and then of course it can only be 0. And so if you have two such objects, theta and eta, and then equal to minus eta theta. And of course, eta squared should also be 0. Okay? So this kind of property make this kind of object very simple. So now we can also talk about the functions of such object. Okay, we can also talk about the function of such object. Say if we have a function f of theta, okay? So we define the function in terms of the power series. So suppose that we have an x, say if you write down a Gaussian function or whatever function, we define this function by the power series. So the power series means that we to the 0th order we have f0 corresponding to theta equal to 0, and then you have f1 theta. Okay, but now if you look at f2 theta squared, that will be 0. So all higher order terms will be 0. So you only have 2 terms. Okay, so the only function of this variable will have 2 terms, a constant term and a term proportional to theta. And then functions of such variables are very simple. Okay. And if you have 2 variables, theta 1 and theta 2, then you just expand until you encounter you have f0 plus f1 theta 1 plus f2 theta 2 and plus f1 2 theta 1 theta 2. That's it. Okay. That's it, because any other term we are involving either theta 1 squared or theta 2 squared, that will be 0. So the differentiation will be extremely simple. So if you take the df theta d theta, so you just, because this is constant, so this is just equal to f1. Okay. But one thing you do have to be careful when you have these multiple variable functions, and then it actually matters whether you take the derivative from the left or take the derivative from the right. Okay, the direction you take the derivative become important. Okay, so so for example, if we take the derivative, let me do it here. So if you take from the left, take the derivative f theta 1 on this f theta 1 theta 2, and then this term is 0. This term gives us f1. This term does not depend on theta 1, and so this term is also 0 when we take the derivative. And here we have theta 1, so we just get f1 2 theta 2. Okay, so this is derivative from the left. But now if I take the derivative from the right, take the derivative from the right, theta 1, okay, take the derivative from the right. So this arrow means you take derivative from the right. And again, the same thing for this one, it doesn't matter, there's only one theta 1. So you just get f1. Again, this 2 will be 0. But now if we take the derivative from the right, then you have to move theta 1 to the right of theta 2 first, because there's a theta 2 here. And that gives you a minus sign. So give you f1 2 theta 2. So you differ by minus sign. Okay. So from now on, without specifically mentioning, we always take derivative from the left. Okay. So the convention, we always take derivative from the left. Yes? Sorry? What do you mean by what type of object? Oh, yeah. They can be complex numbers. They can be real numbers. It's just f0, f1, just some numbers. Yeah. For example, yeah. So suppose f is a Gaussian function. Okay. And then you just write 1. Yeah. It's an exponential theta. 1 plus theta. Okay. It's exponential function just 1 plus. Just to Taylor expansion of theta. And the f0 and 1 just come from the Taylor expansion of whatever function you're looking at. Okay. Yeah, similarly, the same thing, 1 plus theta. So you have a function like that. So you just 1 minus theta. It's very simple, okay? So the functions of these variables are very simple, okay? Good. So we talked about the functions. So we talk about those functions. Also, we talk about the functions of them. We talk about derivatives, and then we need to talk about the integrals of them. Okay. So how to define integration? So now let's talk about how to do integration. So how to do integral? Because we need to do the to be able to do path integral, we need to integrate over such objects. Okay. So to do integration, then we have to specify the rule for integration. Because it's no longer intuitive like derivative, you can just take the derivative. Okay. So integration, we have to specify the rule. And then we use the idea, you should use the standard, the rule for integration, and translate, apply to this case. Okay. So the rules we are going to require for the integration are the following. So the first rule, you said the integration should be linear. Okay, so if I have, say, have an integration of f d theta, I have two functions, f theta a plus g theta b, and a, b are some numbers. They can either be ordinary C numbers, they also can be Grassman numbers, which are anti-commute. Okay, so and then by but the integration operation is linear. This means that this is the same as d theta, f theta times a. Where a is just constant, so you can just take it out the side of the integral. D theta, g theta, b. Okay, so it should be linear, the operation. And the second rule which we require for such integration is that the total derivative should be 0. Okay. So the total derivative should be 0. Okay. And it turns out that these two conditions are can be uniquely then it's enough to actually fix the properties or other properties of the integral. Okay. Yeah, this can be used to fix the integral. Yes?
Why should the total derivative be 0? Like in normal situation, it's only 0 when the boundary vanishes.
Yeah, here we don't have a boundary, so we require it to be 0. Yeah, the theta, yeah, because we don't know how to specify the boundary for theta. Yes?
How does this fix it up to a multiplicative constant? Like, if you take this, it's only multiplied by a half.
Yeah. You say this one?
No, like the whole integral symbol.
Yeah. Sorry, say it again.
Like, suppose like we define this integral like this.
Yeah. Indeed, it does not determine up to, only determine up to a constant. Yeah, but then you can fix that constant. Yeah, I'm going to talk about immediately. Yeah. Good. So we have these two conditions. So let's see what these two conditions tell us. Okay. So from this condition 2, we conclude that d theta f2 equal to 0. Because if we a derivative of f theta, or sorry, just f1 equal to 0. Okay. we write, just f1 equal to 0. And since f1 is a C number, you can take this f1 outside the integral. So that means this is equal to 0. So that means the d theta 1 is equal to 0. Okay? So just d theta, any constant should be 0. Okay. Just any constant should be 0. Okay. So this is the one condition. So one thing we deduce. Okay. So now let's call this property 3, equation 3. This of course follows from the 1 and 2. So now, remember from the property of f theta equal to f0 plus f1 theta. So that means d theta, f theta is equal to d theta f0 plus f1 theta. Okay, so that means, so if you use this property 1, you can take this constant outside it. Okay, then and this term is 0, so you just get the second term. So you just get f1 with theta and the theta. So now if we just fix the value of this object, then we fix the full integral. Okay? And so you just fix this object to be 1. So we just fix, define it to be 1. Okay, define up to a constant, we just define it to be 1. Okay, so that's it. So that's fully specifies the rule. And then we conclude that d theta, f theta is equal to f1. So now you notice, so this is the rule you should remember. So now you notice this is the same as you take the derivative over theta. Okay, so this story is a little bit funny. Okay, so the integration of a function is the same as the derivative over the function. Okay, that's it. So if the calculus for ordinary variables are such simple, when we learn calculus, it will be much easier. And but so these Grassmann variables are very simple. Okay. Any questions on this? Yes.
So what's the point in defining integration this way, without it just being the same as the derivative? Like, is it useful to have both integration and derivatives for these objects? They do the same thing.
Yeah. So this is for the single variable, right? When you go to the multi-variable, then things are a little bit more intricate. Yeah, but this rule will apply. This integration rule is general. Yes.
Why don't we find integral as the opposite of the reverse of the derivative? Because now, for example, integrating and then taking the derivative is not give the same value.
That's right. Yeah, just you don't know how to do that inverse operation anymore. Yeah, just those kind of objects are sufficiently weird. It's not easy. Yeah, so the basic idea, I think, you say why Fermion didn't come up with this. Because if you just say, oh, I have to do anti-commuting, that's not enough. You have to invent the whole calculus for this kind of anti-commuting object. Another question is that how do you invent such a calculus so that it's as natural as possible compared to the standard way? Yeah, so I think this is a set of rules which seems to work very well. Okay. So when we say the Fermion missed it, it's not he missed something just a trivial idea. He missed the whole calculus. Okay. So now let's just make a couple of remarks. So suppose eta is another Grassmann variable, okay? Means that it's also anti-commute. So now if we put eta before f theta, okay? And now, because the eta have nothing to do with theta, you should be able to take it outside the integral. But different variable anti-commute. So when you take eta outside the thing, the rule is that you can just take it out, commute through this d theta, you get the minus sign. So you just get the eta d theta f theta. Okay? So this becomes just f1 eta. So you can show that this rule, which I'm saying here, is compatible with also this rule. Okay, it's also compatible with this rule because you can also commute the eta with f inside the integral, and then you can use this rule, and you can show these two rules are compatible. Okay. So this is the first remark. Second remark is that how to do integration by parts. So now let's consider integral like this. A would be some ordinary, A is just some number. Okay? So you can just expand this trivially. So this just just find this f1 times A. Okay, just find f1 times A. Okay, and of course f1 times A is also the same as A times the theta prime f theta prime. If theta prime is A theta, because it's a dominant variable, doesn't matter. Okay. So this tells you. So then comparing these two. Okay, so this is like a change of variable. Okay. Yes.
So if eta has to obey anti-commutation of theta, why doesn't beta have to obey anti-commutation of theta?
Theta does have to. Yeah.
But then why isn't it?
Oh, but d theta and theta are two different objects, right? They anti-commute with each other, but d theta means the infinitesimal variation of theta. Of course, even though we cannot quantify what this infinitesimal variation means, and but these two are different objects. Yeah, so their product is not there. Okay, good. So this tells you. So normally when we do a change of variable, so this means, let's see, when you do the change of variable theta prime equal to A theta, and d theta prime is actually equal to 1 over A d theta. Okay, if you compare these two. So now this is a very, so now again, this is opposite to the standard story, okay? So the d theta prime is actually equal to 1 over A theta. Okay, so let's conclude here. Yeah, so our next lecture is not next Wednesday, because Monday is a holiday. Yeah, it's a little bit unfortunate. I hope you still remember this when we get to next Wednesday.